Okay, slow motion. The image I attached here is kind of misleading. Capturing such footage requires a very fast camera that shoots a very high frame rate. But let's say you actually have that content that's already shot in a very high frame rate. The way you can see the slow motion, perceive the slow motion, is by playing it in a different frame rate, just normal, maybe just a different lower FPS. And you can do that with normal content as well. It's done in sports all the time, even in gaming, when you want a frame-by-frame explanation to a play. And there are multiple ways to achieve this, and we're going to focus on mainly on the filters that are needed for this and why you'd opt to use them. Okay, so we have two filters and one input method, input arguments. And while all of these methods can be used to change the perceived frame rate, they actually work differently. Instead of comparing them before you know them, we'll explain how to use each of them, and then we'll compare. Okay, if you paid attention to the previous slide, there was no option for an FPS filter because it isn't actually, not on its own, a method for slowing down or speeding up a video. We use the FPS filter to actually change the number of frames and not the speed in which they're perceived. But since it's a lot easier to illustrate and understand, we'll start here. Okay, you know what I love, illustrations that seem to be made by a 90s school kid with paint. So imagine this is a 60 FPS video, and each box here is a frame. We're using the FPS filter to make it into a 30 FPS video. Okay, see, I'll annotate. This is the filter, and this is the one argument it gets 30. So I'm changing from 60 to 30. Okay, so what you would get here, the filter would consider the duration of each frame and basically drop the extras. These are not extras. They contain data, and that data will be lost. And you might not need the data because you only need the 30 FPS video. And for that purpose, this is useful, and I do the same thing. But that's the reason I postpone doing such a thing until the very end, because again, I'm losing data. And when you play back this video, it isn't actually any faster or any slower. It just has less frames, but each of them lingers for longer. Let's assume we're doing the opposite. We have a 30 FPS video, see 30, and we want to generate a 60 FPS video. We'll just change the sole argument here from 30 to 60. The result we'll get here in this scenario, the filter will just duplicate each frame, actually bloating the video with extra frames, and extra data means that this is a larger file now. It's almost twice as big. We'll get into, in another presentation, we'll get into why it's almost twice as big. So the higher frame rates, again, no difference, neither in duration nor speed, just more frames that linger for a shorter period. Okay, the setpts filter. FFmpeg works on every layer of media, and different codecs and formats have different containers that abstract the data in different ways. But when we're using the filter graph, we're almost always accessing the decoded frames that represent the final result, and those frames will have this something, the presentation timestamp. They always have this. So the values will differ a lot between these different codecs and formats, but it's meaningless to us in regards to this task. We don't care if the value is 50 or 50,000. We manipulate it relatively to its previous value. Okay. So we have a 60 FPS video, and we want to add a slow motion effect to its entirety. And the way this actually works isn't some link that says how long it should be. It's actually the frame itself that holds a number, and each consecutive frame just has a larger number, and the delta is the duration. But I think you'd agree that it's much easier to understand it like this. So for the filter itself, setpts only takes a single argument. This part is the argument, of course. and it's always an eval expression, and that will be evaluated per frame. PTS, this part, this constant, it's not actually a constant, it represents the value for the current frame before we're manipulating it. And the expression's result is the value for the current frame after the filter has done its course. Next. So if we double the PTS of all frames, that means the deltas are twice as big, meaning each frame will linger for twice as long. And now we have a 30 FPS video. Okay.